Hello there, and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened. Because tonight, we're going to explore something truly mind-bending. We're going to imagine what it would be like to navigate through a maze made of black holes. Now, you might be thinking, black holes are dangerous, they're mysterious, they pull everything in. How could you navigate through them? Black holes are more than just cosmic vacuum cleaners. They're complex structures. They bend space and time. They create paths. They create mazes. And understanding them might just help us understand the universe itself. You'll hear about objects so dense that light can't escape. You'll learn about event horizons and singularities. You'll discover how black holes create gravitational mazes in space. You'll explore what would happen if you tried to navigate through them. And you'll imagine what it would be like to travel through these cosmic puzzles. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now, let's begin. Chapter 1. What is a black hole? The cosmic puzzle begins. Imagine an object so dense that nothing can escape it. Not even light, not even the fastest thing in the universe. That's a black hole. A region of space where gravity is so strong that it creates a point of no return. Once you cross that boundary, you can't come back. Not ever. It's like falling into a bottomless pit, but in space. And the pit is made of gravity itself. The idea of black holes is actually very old. Over 200 years ago, in 1783, a scientist named John Mitchell imagined something he called dark stars. He thought there might be objects so massive that light couldn't escape from them. He was using the physics of his time, but he was on the right track. Around the same time, a French mathematician named Pierre-Simon Laplace had the same idea. They were the first people to imagine what we now call black holes. But it took over 100 years for scientists to really understand how black holes could form. Black holes form when massive stars die. A star shines by fusing hydrogen into helium. This process releases energy. It pushes outward. It balances the star's gravity. The star stays stable. But eventually, the hydrogen runs out. The star starts fusing heavier elements. Helium becomes carbon. Carbon becomes oxygen, and so on, until it reaches iron. Iron can't be fused to release energy. When a star's core becomes iron, fusion stops. Without fusion, the star's core collapses. It shrinks from the size of Earth to the size of a city, then smaller, much smaller. The gravity becomes overwhelming. If the star is massive enough, nothing can stop the collapse. The core keeps shrinking. It becomes infinitely dense, a point called a singularity. Around this point, space and time are so warped that nothing can escape, not even light. This is a black hole. The boundary around a black hole is called the event horizon. It's the point of no return. Once you cross it, you can't escape. The gravity is too strong. You would need to travel faster than light to escape. But nothing can travel faster than light. So once you're inside, you're trapped forever. This boundary was discovered by a scientist named Carl Schwarzschild. In 1916, just months after Einstein published his theory of general relativity, Schwarzschild solved Einstein's equations. He found the first mathematical description of a black hole. He discovered the event horizon, the boundary we now know marks the edge of a black hole. Sadly, Schwarzschild died shortly after making this discovery. But his work lives on. Every time we talk about event horizons, we're using his discovery. But here's the interesting part. The event horizon isn't a physical barrier, it's not a wall, it's a boundary in space and time, a point where the escape velocity equals the speed of light. If you could travel at the speed of light, you could escape, but you can't, nothing can. So the event horizon marks the edge of the black hole, the edge of the cosmic maze. Black holes come in different sizes. Stellar black holes form from dying stars. They're about 5 to 50 times the mass of our Sun. They're relatively small, but their gravity is still incredibly strong. Supermassive black holes live at the centers of galaxies. They're millions or billions of times the mass of our Sun. They're huge, and their gravity shapes entire galaxies. Our own galaxy, the Milky Way, has a supermassive black hole at its center. It's called Sagittarius A star. It's about 4 million times the mass of our Sun. But it's quiet now. It's not actively eating material. But it's still there, still pulling, still creating a gravitational maze at the center of our galaxy. A scientist named Andrea Ghez proved this black hole exists. She watched stars orbit an invisible object at our galaxy's center for over 20 years. She tracked their paths, their speeds, their orbits. She proved there must be a supermassive black hole there, one that's 4 million times heavier than our Sun. She won a Nobel Prize for this work. She said the center of our galaxy is a perfect laboratory for studying black holes. It's close enough to study, but far enough to be safe. A perfect place to understand these cosmic puzzles. But Sagittarius A star isn't the only black hole in our galaxy. In 2024, scientists discovered a new black hole. It's called Gaia BH3. It's much closer to us, only 1,926 light-years away. That's still far, but it's in our cosmic neighborhood. This black hole is special. It's 33 times the mass of our Sun. That makes it the heaviest stellar black hole we found in the Milky Way. Most stellar black holes are smaller, maybe 5 to 20 times the mass of our Sun. But this one is huge. It's orbiting a star, a giant star that's poor in metals. This tells us something important, that massive black holes can form in metal-poor environments, that the early universe might have created many of these massive black holes, that the cosmic maze might be even more complex than we thought. Scientists estimate there are about 100 million stellar black holes in our galaxy alone. That's a huge number. But most are invisible. They're not eating anything, they're just drifting through space, creating tiny gravitational mazes wherever they go. Some astronomers think there might be even more. Maybe 100 million is too low. We're still counting, still discovering. The universe is vast. There are billions of galaxies. Each one might have millions of black holes. Some scientists think there could be 40 quintillion black holes in the observable universe. That's a 40 followed by 18 zeros. It's hard to imagine. but it shows how common black holes really are. They're everywhere, creating mazes throughout the cosmos. Black holes don't just pull things in, they also bend space and time. This is called gravity. But black holes bend it so much that space itself becomes curved, like a rubber sheet with a heavy ball on it. The ball creates a dip. Things roll toward it. But with black holes, the dip is so deep that it becomes a hole, a bottomless hole in space. This bending of space creates paths. Some paths lead toward the black hole. Some lead around it. Some lead away. But all paths are curved. All paths are part of the gravitational maze. If you tried to navigate through space near a black hole, you would find yourself following these curved paths. You would be navigating through a maze made of gravity itself. The closer you get to a black hole, the stronger the gravity becomes. At a safe distance, you could orbit it, like a planet orbiting a star. But the closer you get, the faster you need to travel to stay in orbit. At the event horizon, you would need to travel at the speed of light. That's impossible. So you fall in. You become part of the black hole. You become part of the maze. But what if there were multiple black holes? What if you had to navigate through a region of space with several black holes? Each one would create its own gravitational maze. Their mazes would overlap. They would create a complex network of paths. Some paths would lead to safety. Some would lead to capture. Some would lead to escape. This would be a true black hole maze, a cosmic puzzle that would challenge even the smartest navigator. Scientists have discovered binary black holes, two black holes orbiting each other. They create a complex gravitational field. Paths curve around both black holes. Some are stable, some are unstable. Some lead to capture, some lead to escape. Navigating through this would be like solving a maze, a three-dimensional maze in space. In 2024, astronomers did something amazing. They took the first picture of two black holes orbiting each other. These black holes are about 5 billion light-years away. That's incredibly far. But we can see them. The bigger black hole is huge. It's 18 billion times the mass of our Sun. That's almost impossible to imagine. The smaller black hole orbits around it. They complete one orbit every 12 years. That's a long orbit. But for black holes this massive, it's actually quite fast. This system is called OJ287. It's a special kind of object called a blazar. The smaller black hole creates a jet, a stream of particles shooting out at nearly the speed of light. This jet twists and turns as the black holes orbit. Scientists have been watching this system for decades. They've seen the jet change direction. They've seen it brighten and dim, all because of the orbital dance of these two black holes. This is the first time we've actually seen two black holes orbiting each other. It's visual proof that binary black holes exist, that they create complex gravitational mazes, that they're part of the cosmic puzzle. Before 2015, we had never directly detected black holes merging. We thought it happened, but we had no proof. Then LIGO detected the first gravitational waves from two black holes colliding. It was September 14, 2015, a historic day. The signal lasted only 0.2 seconds, but it changed everything. It proved black holes really do merge. It proved Einstein was right about gravitational waves. It opened a new way to study the universe. Now, we've detected over 90 mergers. Each one teaches us something new. Each one helps us understand the mazes better. The first detection was called GW150914. That's a code name. GW stands for gravitational wave. 1509 means September 14, 2015. The two black holes that merged were about 29 and 36 times the mass of our Sun. They merged into one black hole that was 62 times the mass of our Sun. But wait, that doesn't add up. 29 plus 36 is 65. Where did the extra 3 solar masses go? They were converted into energy, into gravitational waves. In just 0.2 seconds, these black holes released more energy than all the stars in the observable universe combined. That's how powerful these mergers are. That's how much energy is in a black hole maze. Since that first detection, LIGO and its partner Virgo have detected over 90 black hole mergers. Each one is different. Some involve small black holes. Some involve huge ones. In 2025, scientists detected the most massive merger ever recorded. 2 black holes, each about 100 and 140 times the mass of our Sun, merged into one monster black hole that was 225 times the mass of our Sun. This was special because these black holes were in a mass gap. Scientists didn't think black holes this size could form from dying stars. But there they were, merging, creating gravitational waves, teaching us that we still have a lot to learn. The paths in a black hole maze aren't random. They follow the laws of physics. They're determined by gravity, by the curvature of space, by the motion of the black holes themselves. If you understood these laws, you could calculate the paths. You could find safe routes. You could navigate the maze, in theory at least. But in practice, it would be incredibly difficult. The gravitational fields are complex. They change over time. The black holes move. Their mazes shift. What was a safe path one moment might become a trap the next. You would need to constantly recalculate, constantly adjust, constantly navigate. It would be like solving a maze that keeps changing, a puzzle that never stays still. Black holes also create something called an ergosphere. It's a region outside the event horizon where space itself is dragged around the black hole, like water being pulled by a whirlpool. If you entered the ergosphere, you would be dragged along. You couldn't stay still. You would be forced to move. You would be part of the rotation, part of the cosmic dance. The ergosphere adds another layer to the maze. Not only do you need to avoid falling in, but you also need to avoid being dragged around. You need to find paths that don't enter the ergosphere, or paths that enter and exit safely. It's like a maze with moving walls, walls that pull you along, walls that you can't resist. Black holes also emit radiation. This is called Hawking radiation. It's named after Stephen Hawking, who discovered it in 1974. Hawking made an amazing discovery. He showed that black holes aren't completely black. They glow. Very faintly, but they glow. This shocked everyone. Before Hawking, scientists thought black holes were completely dark. Nothing could escape. But Hawking showed that quantum effects near the event horizon create radiation. The black hole slowly loses mass, very slowly, but it's losing mass. Hawking radiation is very weak. For a stellar black hole, it would take trillions of years to evaporate, but it's still there. It's still happening. And it adds another element to the maze. radiation that you need to avoid or use, depending on your strategy. Hawking's discovery changed how we think about black holes. They're not eternal prisons. They can evaporate over incredibly long times, but they can disappear. This was a revolutionary idea. The radiation comes from quantum effects near the event horizon. Virtual particles appear and disappear. Sometimes one particle falls into the black hole while the other escapes. The escaping particle becomes real radiation. The black hole loses mass, very slowly, but it's losing mass. It's shrinking, very slowly, but it's shrinking. This means black holes aren't eternal. They eventually evaporate, but it takes an incredibly long time, longer than the age of the universe. So for practical purposes, black holes are permanent. They're permanent features of the cosmic maze, permanent puzzles to solve. Black holes also create gravitational waves. When two black holes orbit each other, they create ripples in space-time. These ripples travel outward at the speed of light. They carry energy away. The black holes spiral closer together. Eventually, they merge. They become one larger black hole. This merger creates a burst of gravitational waves, a signal that we can detect on Earth. Gravitational waves were first detected in 2015 by the LIGO Observatory. It was a historic moment. It confirmed Einstein's theory of general relativity. It opened a new window into the universe, and it showed us that black holes are constantly merging, constantly creating new mazes, constantly changing the cosmic puzzle. The LIGO project was led by scientists like Kip Thorne. He spent decades studying black holes. He helped build the machines that could detect gravitational waves. When LIGO finally detected the first waves, it was a triumph. Thorne once said that black holes are the most perfect objects in the universe. They're simpler than atoms, simpler than stars, simpler than galaxies. They're just pure gravity, pure space-time curvature. And that simplicity makes them beautiful. Thorne also worked on the movie Interstellar. He helped create the black hole called Gargantua. He wanted it to be scientifically accurate. He calculated how light would bend around it, how time would slow down, how the accretion disk would look. The result was stunning. A black hole that looked real, that looked like what we might actually see. Thorne said that working on the movie helped him think about black holes in new ways. It showed him how art and science can work together, how imagination can help us understand reality. But here's something interesting. While Thorne thinks black holes are perfect and simple, other scientists disagree. Some think black holes are incredibly complex. They think black holes might be made of tangled strings, of multi-dimensional mazes, of structures we can't even imagine. This is called string theory. It's a different way of thinking about black holes. It suggests that inside a black hole there might be a supermaze, a complex network of paths, a structure that's anything but simple. Scientists are still debating this, still learning, still exploring. The detection of gravitational waves also showed us that black hole mazes are dynamic. They're not static. They change, they evolve. Black holes merge, they grow, they create new gravitational fields, new mazes, new puzzles to solve. So, a black hole maze isn't just a collection of black holes. It's a living, changing system. A system that evolves over time. A system that creates new challenges, new paths, new mysteries. It's a cosmic puzzle that never stays the same. A maze that keeps changing. Understanding black holes is like learning to read a map, but the map is three-dimensional, and it's constantly changing. And the paths are determined by gravity, by the curvature of space, by the laws of physics. It's a complex puzzle, but it's also beautiful. It's a testament to the power of gravity, to the structure of space and time, to the universe itself. Black holes are mysterious, but they're also understandable. They follow the laws of physics. They create patterns. They create mazes. And with enough knowledge, enough skill, enough luck, you might just be able to navigate through them. You might just be able to outsmart the black hole maze. Chapter 2. The Event Horizon. Crossing the Point of No Return. The event horizon is the boundary of a black hole. It's the point of no return. Once you cross it, you can't escape. Not ever. But what exactly happens at the event horizon? What would you see? What would you feel? And could you use this knowledge to navigate through a black hole maze? The event horizon isn't a physical surface. It's not a wall. It's a boundary in space and time, a point where the escape velocity equals the speed of light. If you were falling toward a black hole, you wouldn't feel anything special when you crossed it. You wouldn't hit a wall. You wouldn't see a barrier. You would just keep falling. But once you crossed it, you couldn't turn back. You couldn't escape. Scientists have actually tested this idea. Not with real black holes, of course, but with computer simulations, with mathematical models. They've calculated what would happen to someone falling into a black hole. The calculations show that you wouldn't feel anything special at the event horizon. You would just keep falling. But from the outside, you would appear to freeze. Your light would get stretched. You would fade away. This is called gravitational redshift. It's a real effect. We've seen it happen to light from stars near black holes. The light gets stretched. It becomes redder. It loses energy. This is how we know the event horizon is real, how we know it's not just a theory. From your perspective, falling into a black hole, the event horizon would seem normal. You would just keep falling. But from an outside observer's perspective, something strange would happen. As you approach the event horizon, you would appear to slow down. Your light would be redshifted, stretched to longer wavelengths. You would appear to freeze at the event horizon. You would never actually cross it from their perspective. This is called time dilation. Time moves slower near a black hole. The stronger the gravity, the slower time moves. At the event horizon, time stops. From an outside perspective, at least. But from your perspective, time would continue normally. You would cross the event horizon, you would keep falling. You would reach the singularity, eventually. The event horizon creates a one-way door. You can go in, but you can't come out. This is crucial for navigating a black hole maze. You need to avoid crossing event horizons. You need to stay outside them. You need to find paths that curve around them, that avoid them, that keep you safe. The size of the event horizon depends on the mass of the black hole. For a stellar black hole, the event horizon might be only a few kilometers across. That's small, but the gravity is still incredibly strong. For a supermassive black hole, the event horizon might be millions of kilometers across. That's huge, but the gravity at the event horizon is the same. It's always strong enough to trap light. There's a formula for this. It's called the Schwarzschild radius, named after Karl Schwarzschild, who discovered it. The formula is simple. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers across. That's tiny, smaller than most cities. But if you had a black hole that was 10 times the mass of our Sun, the event horizon would be 30 kilometers across. If it was 100 times the mass, it would be 300 kilometers across. The size grows with the mass, but the density at the event horizon stays the same. It's always strong enough to trap light, always strong enough to create a point of no return. For Sagittarius A star, our galaxy's supermassive black hole, the event horizon is about 24 million kilometers across. That's huge, about 17 times the size of our Sun. But it's still tiny compared to the galaxy. The galaxy is 100,000 light-years across. The event horizon is just a tiny dot at the center. But that tiny dot controls the entire galaxy. It shapes the orbits of billions of stars. It creates the gravitational maze that defines our cosmic neighborhood. The shape of the event horizon also matters. For a non-rotating black hole, it's a perfect sphere, simple, symmetric. But for a rotating black hole, it's more complex. It's flattened at the poles, it's wider at the equator. It's like a spinning top. This shape affects the paths around it. It affects the maze. A rotating black hole also has 2 event horizons, an outer one and an inner one. The region between them is called the ergosphere. It's a region where space itself is dragged around. You can't stay still there. You're forced to rotate. This creates additional complexity in the maze, additional paths, additional challenges. The event horizon also has 2 event horizons, an outer one and an inner one. The region between them is called the ergosphere. It's a region where space itself is dragged around. You can't stay still there. You're forced to rotate. This creates additional complexity in the maze, additional paths, additional challenges. The event horizon also creates something called the photon sphere. It's a region just outside the event horizon where light can orbit the black hole. Photons, particles of light, can travel in circular paths. They're trapped, not falling in, but not escaping either. They're orbiting forever. The photon sphere is like a ring of light around the black hole. It's beautiful, but it's also dangerous. If you got too close, light from behind you would orbit around and hit you from the front. You would see multiple images of the same object. You would see the back of your own head. The geometry would be strange, confusing, like a hall of mirrors. For navigation, the photon sphere marks a critical boundary. Inside it, light can't escape. Outside it, light can escape. But the paths are still curved, still part of the maze. You need to stay well outside the photon sphere to be safe, to have clear paths, to navigate effectively. The event horizon also creates tidal forces. These are forces that stretch and compress objects. Near a black hole, the gravity on your feet would be stronger than the gravity on your head. You would be stretched, like spaghetti. This is called spaghettification. It's not pleasant, and it happens before you even reach the event horizon. For small black holes. For a stellar black hole, you would be spaghettified well outside the event horizon. The tidal forces would be too strong. You would be torn apart. But for a supermassive black hole, the event horizon is much larger. The tidal forces are weaker. You might survive crossing the event horizon. You might fall in intact, but you still couldn't escape. You would still be trapped. Scientists have calculated exactly where this would happen. For a black hole that's 10 times the mass of our Sun, you would be torn apart about 600 kilometers from the event horizon. That's well outside. You would never even get close. But for Sagittarius A star, our galaxy's supermassive black hole, you could cross the event horizon safely. The tidal forces wouldn't tear you apart until you were much closer to the center. You might have hours or even days before you were spaghettified, but you still couldn't escape. The event horizon is still a one-way door. Once you're inside, you're trapped forever. This difference is important for navigation. If you're trying to navigate through a black hole maze, you need to know which black holes are safe to approach, which ones will tear you apart from far away, which ones you might be able to get closer to. It's all about the size. The bigger the black hole, the safer it is to approach. But safe doesn't mean you can escape. It just means you won't be torn apart immediately. Tidal forces are important for navigation. They tell you how close you can safely get. They define the safe zone, the region where you can navigate without being torn apart. This safe zone is part of the maze. It's the region where navigation is possible, where you can find paths, where you can outsmart the black hole. The event horizon also affects how you see things. Light from objects behind the black hole would be bent. It would curve around. You would see distorted images, multiple images. The black hole would act like a lens, a gravitational lens. It would magnify and distort everything behind it. For navigation, the lensing effect would be both helpful and confusing. Helpful because it would show you objects behind the black hole, confusing because the images would be distorted. You would see multiple copies of the same object. You would need to interpret what you're seeing. You would need to understand the geometry. The event horizon also creates something called the innermost stable circular orbit. It's the closest you can orbit a black hole without falling in. For a non-rotating black hole, it's 3 times the radius of the event horizon. For a rotating black hole, it's closer, much closer. You could orbit almost at the event horizon itself. The innermost stable circular orbit is important. It defines the edge of the safe zone, the region where stable orbits are possible, where you can navigate, where you can find paths, where you can outsmart the black hole. Inside the innermost stable circular orbit, all paths lead inward. There are no stable orbits, no safe paths. You would spiral inward. You would fall toward the event horizon. You would be captured. You would become part of the black hole. So for navigation, you need to stay outside the innermost stable circular orbit. You need to find paths that curve around it, that avoid it, that keep you safe. This is the challenge of the black hole maze. Finding paths that stay in the safe zone, that avoid the traps, that lead to your destination. The event horizon also creates gravitational time dilation. Time moves slower near it. The closer you get, the slower time moves. From your perspective, time would seem normal, but from an outside perspective, you would appear to slow down. You would appear to freeze at the event horizon. This time dilation affects navigation. If you're near a black hole, time moves slower for you. Your clocks run slow. Your processes slow down. But the universe around you continues at normal speed. This creates a disconnect, a challenge. You need to account for this. You need to adjust your navigation. The event horizon also creates frame dragging. For rotating black holes, space itself is dragged around, like water in a whirlpool. This dragging affects all paths, all orbits, all navigation. You can't escape it. You're part of the rotation, part of the cosmic dance. Frame dragging creates additional paths, paths that follow the rotation, paths that are dragged along. These paths are part of the maze. They're options, they're possibilities, but they're also constraints. You can't move against the rotation. You're forced to follow it, at least near the black hole. The event horizon is also where information is lost. According to quantum mechanics, information can't be destroyed. But according to general relativity, information that falls into a black hole is lost forever. This is called the information paradox. It's one of the biggest mysteries in physics. For navigation, the information paradox isn't directly relevant, but it shows us that black holes are mysterious, that they challenge our understanding, that they're complex puzzles, that navigating through them would require understanding things we don't fully understand yet. The event horizon is the key to the black hole maze. It defines the boundaries. It creates the paths. It determines what's possible and what's not. Understanding the event horizon is like understanding the walls of a maze. Once you understand them, you can find your way through. You can navigate. You can outsmart the black hole. But the event horizon is just the beginning. There's more to the maze, more paths, more challenges, more mysteries. The event horizon is the first layer, the outer layer, but there are deeper layers, more complex layers, layers that we're only beginning to understand. Chapter 3: Navigating the Gravitational Maze. Paths through curved space. Space near a black hole is curved, like a rubber sheet with a heavy ball on it. The ball creates a dip. Things roll toward it. But with black holes, the dip is so deep that it becomes a hole, a bottomless hole in space. And this curvature creates paths. Some paths lead toward the black hole. Some lead around it. Some lead away. But all paths are curved. All paths are part of the gravitational maze. If you tried to navigate through space near a black hole, you would follow these curved paths. You wouldn't travel in straight lines. You couldn't. Space itself is curved. So your path curves. It follows the geometry of space. It follows the gravitational maze. The paths in a black hole maze aren't random. They follow the laws of physics. They're determined by gravity, by the curvature of space, by Einstein's theory of general relativity. If you understood these laws, you could calculate the paths. You could find safe routes. You could navigate the maze, in theory at least. Interestingly, Einstein himself wasn't sure black holes were real. His equations predicted them, but he thought nature would prevent them from forming. He thought they were just mathematical curiosities, not real objects. But in 1939, two scientists named J. Robert Oppenheimer and Hartland Snyder calculated exactly how a star would collapse into a black hole. They showed it was possible. They proved black holes could form. Even Einstein was wrong about this one. Sometimes the math shows us things we don't expect. Oppenheimer and Snyder's calculation was groundbreaking. They showed that when a massive star runs out of fuel, nothing can stop its collapse. The star shrinks and shrinks and shrinks until it becomes a point, a singularity. They calculated this using Einstein's equations. The math was clear. Black holes had to form. But many scientists didn't believe it. They thought something would prevent the collapse. They thought nature would find a way to stop it. But nature didn't. The math was right. Black holes are real. But here's something interesting. While Oppenheimer and Snyder showed that black holes could form, they didn't know if they actually existed. They had no way to detect them. Black holes are invisible. They don't emit light. They don't reflect light. They just sit there, pulling, creating gravitational mazes, but invisible. It took decades before we found ways to detect them, to prove they were real, to see their effects on the universe around them. But in practice, it would be incredibly difficult. The gravitational fields are complex. They change over time. The black holes move. Their mazes shift. What was a safe path one moment might become a trap the next. You would need to constantly recalculate, constantly adjust, constantly navigate. The simplest path around a black hole is an orbit, like a planet orbiting a star. But the orbits near black holes are different. They're not perfect circles. They're ellipses, and they precess. They rotate. The point of closest approach shifts. The orbit itself rotates around the black hole. This precession is called the advance of the perihelion. It was one of the first tests of general relativity. Mercury's orbit precesses, and Einstein's theory explained it. Near black holes, the precession is much stronger. The orbits rotate faster. The paths are more complex. For navigation, precession means that orbits aren't stable. They change over time. What was a safe orbit might become dangerous. You would need to adjust. You would need to find new paths. You would need to constantly navigate. There are also unstable orbits, orbits that seem safe but aren't. Small perturbations would send you spiraling inward or outward. These orbits are like narrow paths on a cliff. One wrong step and you fall. They're part of the maze, but they're dangerous. They're traps. Stable orbits are safer, but they're also limited. They're constrained. You can't go everywhere. You're limited to certain paths, certain regions. The stable orbits define the navigable space, the region where you can safely travel, the region where you can outsmart the black hole. But what if you need to go somewhere that's not on a stable orbit? What if you need to cross from one orbit to another? You would need to use thrust. You would need to change your velocity. You would need to burn fuel. And fuel is limited, so you would need to be efficient. You would need to find the most efficient paths. The most efficient path between two orbits is called a Hohmann transfer. It's an elliptical orbit that touches both orbits. It's the path that requires the least fuel. But near a black hole, Hohmann transfers are more complex. The gravity is stronger. The paths are more curved. The transfers require more fuel, or more time, or both. There are also gravity assists, using the gravity of one object to change your velocity, to gain speed, or to change direction. Near a black hole, gravity assists could be powerful. The gravity is strong. You could gain a lot of speed, but you would also risk being captured. You would need to be careful. You would need to calculate precisely. Gravity assists are like using the walls of a maze to bounce, to change direction, to gain momentum. They're part of the navigation strategy, part of outsmarting the black hole. But they're also risky. One miscalculation and you're trapped. There are also Lagrange points, points where the gravity of multiple objects balances, where you can stay in a stable position. Near a black hole, Lagrange points would be complex. The gravity is strong. The points would shift. They would be unstable. But they might still be useful. They might still be part of the maze. For a binary black hole system, Lagrange points would be especially interesting. Two black holes orbiting each other. Their gravitational fields overlap. They create complex patterns. Some regions are stable, some are unstable. Some lead to capture, some lead to escape. These regions define the maze. They create the paths. They determine what's possible. The L4 and L5 Lagrange points are stable. They're like safe zones, islands in the gravitational sea. You could stay there. You could use them as waypoints, as rest stops, as part of your navigation strategy. But the L1, L2, and L3 points are unstable. They're like mountain passes. You can cross them, but you can't stay. Small perturbations would push you away. They're part of the maze, but they're challenging. They require precise navigation. There are also chaotic regions. Regions where small changes in initial conditions lead to large changes in outcome. Where prediction is impossible. Where paths are unpredictable. These regions are like mazes within mazes. Complex puzzles, unpredictable challenges. Chaotic regions are dangerous. You can't predict what will happen. You can't plan. You can only react. You can only hope. But they might also be useful. They might create unexpected paths, unexpected opportunities. They might be shortcuts, or they might be traps. You wouldn't know until you tried. There are also escape trajectories, paths that lead away from the black hole, that allow you to escape, that take you to safety. These are the most important paths, the paths you need to find, the paths that let you outsmart the black hole. Escape trajectories require enough velocity, enough energy. You need to reach escape velocity, the velocity needed to escape the gravitational pull. For a black hole, escape velocity at the event horizon is the speed of light. That's impossible. But farther out, escape velocity is lower. You can escape, if you have enough speed. The escape velocity decreases with distance. The farther you are, the easier it is to escape. So escape trajectories start far from the black hole. They curve around it. They use gravity to gain speed. They slingshot around, and they escape. They lead to safety. But finding escape trajectories isn't easy. The paths are curved. They're complex. They require precise calculations, and they change over time. As the black holes move, as their mazes shift, you would need to constantly recalculate, constantly adjust, constantly navigate. There are also capture trajectories, paths that lead into the black hole, that result in capture, that are traps. These are the paths you need to avoid, the paths that would end your journey, the paths that would make you part of the black hole. Avoiding capture trajectories is crucial. You need to stay outside the event horizon. You need to stay in the safe zone. You need to find paths that curve around, that avoid the traps, that keep you safe. There are also periodic orbits, orbits that repeat, that return to the same point. These are like loops in the maze. You could follow them, you could use them, but you would also be going in circles. You would need to break out, to find new paths, to continue your journey. Periodic orbits are stable, they're predictable, they're safe, but they're also limiting. They don't take you anywhere new. They're part of the maze, but they're not the solution. They're not the way out. There are also homoclinic orbits, orbits that approach a periodic orbit, that get close, but then diverge. They're like paths that almost loop, but don't quite. They're complex, they're beautiful, they're part of the maze, but they're also challenging. They require precise navigation. Homoclinic orbits are unstable. Small perturbations would change them dramatically. They're like balancing on a knife edge. One wrong move and you fall. They're part of the maze, but they're dangerous. They're traps. There are also heteroclinic orbits, orbits that connect two different periodic orbits, that provide transitions, that create paths between different regions. These are like bridges in the maze. They connect different parts. They create new possibilities. Heteroclinic orbits are useful. They provide routes. They create options. They're part of the navigation strategy, part of outsmarting the black hole. But they're also complex. They require precise calculations. They require careful navigation. The paths in a black hole maze are three-dimensional. They curve through space. They're not flat. They're not simple. They're complex. They require three-dimensional thinking, three-dimensional navigation, three-dimensional problem-solving. The paths also change over time, as the black holes move, as they orbit each other, as they merge. The maze evolves. The paths shift. What was safe becomes dangerous. What was a trap becomes an opportunity. The maze is dynamic. It's alive. It's constantly changing. Navigating a black hole maze would require constant attention, constant calculation, constant adjustment. You couldn't set a course and forget it. You would need to monitor, to update, to adapt. The maze would challenge you. It would test your skills. It would push you to your limits. But it would also be possible, in theory at least. The paths exist. They follow the laws of physics. They're calculable. They're navigable. With enough knowledge, enough skill, enough technology, you might just be able to outsmart the black hole maze. Chapter 4: Multiple Black Holes, the Ultimate Cosmic Maze. What if you had to navigate through a region with multiple black holes? Each one would create its own gravitational maze. Their mazes would overlap. They would create a complex network of paths. Some paths would lead to safety. Some would lead to capture. Some would lead to escape. This would be the ultimate black hole maze, a cosmic puzzle that would challenge even the smartest navigator. The simplest multi-black hole system is a binary. Two black holes orbiting each other. They create a complex gravitational field. Paths curve around both black holes. Some paths are stable. Some are unstable. Some lead to capture. Some lead to escape. Navigating through this would be like solving a maze, a three-dimensional maze in space. Binary black holes are common. Many stars are in binary systems. When they die, they can become binary black holes. These systems are stable. The black holes orbit each other. They can orbit for billions of years, until they merge. Until they merge. The orbits of binary black holes are complex. They're not simple circles. They're ellipses. And they precess. They rotate. The orbits themselves evolve. They lose energy to gravitational waves. They spiral closer together. Eventually, they merge. As binary black holes spiral together, their gravitational field changes. The mazes shift. The paths change. What was stable becomes unstable. What was safe becomes dangerous. The maze evolves. it becomes more complex, more challenging. The merger of two black holes is one of the most powerful events in the universe. It releases enormous amounts of energy in gravitational waves, in a burst that we can detect on Earth. The merger creates a new black hole, a larger one, with a new gravitational field, a new maze. Before the merger, the binary system has two event horizons, 2 points of no return. You need to avoid both. You need to find paths that curve around both, that stay safe, that keep you away from both traps. The region between the two black holes is especially complex. Their gravitational fields overlap. They create a region of strong gravity, a region where paths are highly curved, where navigation is difficult, where the maze is most challenging. There are also Lagrange points, points where the gravity of both black holes balances, where you can stay in a stable position. The L4 and L5 points are stable. They're like safe zones, islands in the gravitational sea. You could use them as waypoints, as rest stops, as part of your navigation strategy. But the L1, L2, and L3 points are unstable. They're like mountain passes. You can cross them, but you can't stay. Small perturbations would push you away. They're part of the maze, but they're challenging. They require precise navigation. As the black holes spiral together, the Lagrange points shift. They move. They become unstable. The safe zones disappear. The maze changes. The challenge grows. There are also periodic orbits, orbits that repeat, that return to the same point, around both black holes. These are like loops in the maze. You could follow them, you could use them, but you would also be going in circles. You would need to break out, to find new paths, to continue your journey. Some periodic orbits are stable, they're predictable, they're safe, but they're also limiting. They don't take you anywhere new. They're part of the maze, but they're not the solution. They're not the way out. Other periodic orbits are unstable. Small perturbations would send you spiraling away. They're like narrow paths on a cliff. One wrong step, and you fall. They're part of the maze, but they're dangerous. They're traps. There are also chaotic regions, regions where small changes in initial conditions lead to large changes in outcome, where prediction is impossible, where paths are unpredictable. These regions are like mazes within mazes, complex puzzles, unpredictable challenges. Chaotic regions are especially common in binary systems. The overlapping gravitational fields create complex dynamics. Small changes in position lead to large changes in trajectory. Prediction becomes guesswork. Navigation becomes guesswork. But chaotic regions might also be useful. They might create unexpected paths, unexpected opportunities. They might be shortcuts, or they might be traps. You wouldn't know until you tried, and trying would be risky, very risky. There are also escape trajectories, paths that lead away from both black holes, that allow you to escape, that take you to safety. These are the most important paths, the paths you need to find, the paths that let you outsmart the black hole maze. Escape trajectories are more complex in binary systems. You need to escape from both black holes. You need enough velocity, enough energy. You need to find paths that curve around both, that avoid both traps, that lead to safety. Finding escape trajectories in a binary system is difficult. The paths are curved, they're complex, they require precise calculations, and they change over time. As the black holes orbit each other, as they spiral together, as their mazes shift. There are also capture trajectories, paths that lead into one of the black holes, that result in capture, that are traps. These are the paths you need to avoid, the paths that would end your journey, the paths that would make you part of the black hole. In a binary system, you have two traps to avoid, two event horizons, 2 points of no return. You need to stay away from both. You need to find paths that curve around both, that avoid both traps, that keep you safe. Avoiding capture trajectories is crucial. You need to stay outside both event horizons. You need to stay in the safe zone. You need to find paths that curve around, that avoid the traps, that keep you safe. What about 3 black holes or more? The complexity would increase dramatically. Each additional black hole adds another gravitational field, another maze, another layer of complexity. The paths would become even more curved, even more complex, even more challenging. 3 black holes can form stable systems, but they're rare. Most 3-body systems are unstable. One of the black holes would be ejected. The system would become a binary, or all 3 would merge, or the system would break apart. But if 3 black holes did form a stable system, the gravitational maze would be incredibly complex. 3 overlapping mazes, 3 sets of paths, 3 challenges. Navigation would be nearly impossible. Nearly, but not quite. There are also black hole clusters, groups of black holes orbiting each other. These are even rarer, but they might exist. In the centers of galaxies, where black holes can accumulate, where they can form clusters. A black hole cluster would create the ultimate maze. Multiple overlapping gravitational fields, multiple sets of paths, multiple challenges. Navigation would be incredibly difficult, but it might still be possible. With enough knowledge, enough skill, enough technology. There are also intermediate mass black holes that are larger than stellar black holes but smaller than supermassive ones. They might be hundreds or thousands of times the mass of the Sun. They're mysterious. We're not sure how they form, but they might exist. And they would create their own mazes, their own challenges. Scientists have been searching for intermediate mass black holes for decades. They're hard to find. They're not as common as stellar black holes. They're not as obvious as supermassive ones. But recent discoveries suggest they might exist. In 2020, LIGO detected a black hole that was 142 times the mass of our Sun. That's in the intermediate mass range. It was created by the merger of 2 smaller black holes. This showed that intermediate mass black holes can form through mergers, through growth, through processes we're still learning about. In 2025, scientists at Vanderbilt University made an important discovery. They reanalyzed data from LIGO and Virgo. They looked for black hole mergers. They found evidence of intermediate mass black holes between 100 and 300 times the mass of our Sun. These are the missing links, the bridges between stellar black holes and supermassive ones. Scientists think these might have formed from the first stars, the very first stars in the universe. They were huge, hundreds of times the mass of our Sun. When they died, they might have created these intermediate mass black holes. These black holes then grew, merged, became supermassive. This is one theory, but it's an important one. It connects the early universe to today. It shows how black holes evolve, how the maze grows, how it changes over billions of years. These intermediate mass black holes are crucial for understanding the cosmic maze. They're the stepping stones, the way stations, the links in the chain. Without them, we can't explain how supermassive black holes formed, how they got so big so fast, how they became the monsters we see today. Finding them is like finding missing pieces of a puzzle, pieces that help us understand the whole picture, the whole maze. Some scientists think intermediate mass black holes might be the seeds of supermassive black holes, that they grow over time, that they merge with other black holes, that they eventually become supermassive. This would explain how supermassive black holes formed in the early universe. They started as intermediate mass black holes. They grew, they merged, they became the monsters we see today. This is still a theory, but it's an interesting one. It connects different types of black holes. It shows how the maze evolves, how it grows, how it changes over time. A system with multiple black holes of different sizes would be especially complex. The larger black hole would dominate, but the smaller ones would create perturbations. They would add complexity. They would make the maze more challenging. There are also black hole binaries with different masses, one large, one small. The larger one would dominate the gravitational field, but the smaller one would create perturbations. It would add complexity. It would make the maze more interesting. The paths in a multi-black hole system are three-dimensional. They curve through space, around multiple objects. They're not flat. They're not simple. They're complex. They require three-dimensional thinking, three-dimensional navigation, three-dimensional problem-solving. The paths also change over time, as the black holes orbit each other, as they spiral together, as they merge. The maze evolves. The paths shift. What was safe becomes dangerous. What was a trap becomes an opportunity. The maze is dynamic. It's alive. It's constantly changing. Navigating a multi-black hole maze would require constant attention, constant calculation, constant adjustment. You couldn't set a course and forget it. You would need to monitor, to update, to adapt. The maze would challenge you. It would test your skills. It would push you to your limits. But it would also be possible, in theory at least. The paths exist. They follow the laws of physics. They're calculable. They're navigable. With enough knowledge, enough skill, enough technology, you might just be able to outsmart the ultimate black hole maze. Chapter 5. What would happen if you tried? The reality of navigation. So, what would really happen if you tried to navigate through a black hole maze? What challenges would you face? What dangers? What possibilities? Let's imagine. Let's explore. Let's see what the reality would be. First, you would need a spacecraft. A fast one, a maneuverable one that could change direction quickly, one that could accelerate and decelerate, one that could navigate through curved space, through the gravitational maze. Your spacecraft would need powerful engines to change velocity, to escape gravitational pulls, to navigate. But fuel is limited. You can't carry infinite fuel, so you would need to be efficient. You would need to find the most efficient paths, the paths that require the least fuel. You would also need precise navigation systems to know where you are, to know where the black holes are, to calculate the paths, to predict the future. Navigation near black holes is complex. It requires precise calculations, precise measurements, precise control. You would need to know the positions of all the black holes, their masses, their velocities, their orbits. Any uncertainty would lead to errors, errors that could be fatal. You would need perfect information, or as close to perfect as possible. But perfect information is impossible. There's always uncertainty, always error, always noise. You would need to account for this. You would need to be conservative. You would need to leave margins. You would need to be safe. You would also need to account for time dilation. Time moves slower near black holes. Your clocks would run slow. Your processes would slow down. But the universe around you would continue at normal speed. This creates a disconnect, a challenge. You would need to account for this. You would need to adjust your navigation. Time dilation would also affect communication. If you tried to communicate with someone far away, your messages would be delayed. They would be redshifted. They would be distorted. You would be operating in isolation. You would be on your own. You would also face tidal forces. The gravity on one side of your spacecraft would be stronger than on the other. You would be stretched, compressed, twisted. Your spacecraft would be stressed. It might break. It might fail. You would need a strong spacecraft, one that could withstand the forces. For a stellar black hole, tidal forces would be strong. You would be torn apart well outside the event horizon. But for a supermassive black hole, the event horizon is much larger. Tidal forces are weaker. You might survive, but you still couldn't escape. You would still be trapped. You would also face radiation. Black holes can have accretion disks, disks of hot gas falling in. These disks are bright. They emit X-rays. They're dangerous. You would need to avoid them, or shield yourself, or both. Accretion disks are incredibly hot. The gas falling into a black hole gets compressed. It heats up to millions of degrees, sometimes billions of degrees. At these temperatures, the gas glows. It emits X-rays. It emits gamma rays. It's incredibly bright, brighter than entire galaxies. The Chandra X-ray Observatory has detected these disks. It's seen the X-rays they emit. It's mapped their structure. These disks are real. They're dangerous. They're part of the black hole maze. But there's more than just the accretion disk. Black holes also have something called a corona. It's a superheated halo of gas. It surrounds the black hole. It's incredibly hot, even hotter than the accretion disk. Scientists have been trying to study coronas for years, but they're hard to see. They're small. They're far away. But in 2024, something amazing happened. Scientists got lucky. They used a technique called gravitational lensing. A galaxy in front of a black hole bent its light, made it brighter, made it easier to see. But then something even more amazing happened.
Stars in that foreground galaxy also bent the light, created a double zoom effect, like looking through two magnifying glasses. This let scientists see the corona in incredible detail. They could measure its size. They could study its structure. They could understand how it works. This black hole is called RxJ 1131. It's 6 billion light-years away. But we can see its corona. We can study it. We can understand it. This discovery helps us understand magnetic fields around black holes, how they grow, how they create the maze.
But not all black holes have accretion disks. Most black holes are quiet. They're not eating anything. They're just drifting through space, creating gravitational mazes, but not glowing, not emitting radiation. These quiet black holes would be safer to navigate around, but they would also be harder to detect, harder to map, harder to avoid. You might not know they're there until you're too close, until you're already caught in their gravitational maze. Scientists have discovered that accretion disks can be huge. For a supermassive black hole, the disk can be light-years across. That's enormous. The disk around Sagittarius A star, if it were active, could stretch from here to the nearest star. That's 4 light-years. A huge, glowing disk of hot gas, spinning, falling in, creating a dangerous zone around the black hole, a zone you would need to avoid or navigate through very carefully. There's also Hawking radiation, very weak but still there, and cosmic rays, high-energy particles, from the black hole, from the galaxy, from the universe. You would be bombarded. You would need protection. You would need shielding. You would also face the problem of fuel. Fuel is heavy. The more fuel you carry, the more you need to accelerate it. The more fuel you need. It's a vicious cycle. You would need to be efficient. You would need to use gravity assists. You would need to find the most efficient paths. But gravity assists are risky. You might be captured. You might fall in. You would need to calculate precisely. You would need to be careful. You would need to be lucky. You would also face the problem of time. Navigation takes time. The paths are long. They curve around. They take you far. You would need patience. You would need endurance. You would need supplies, food, water, air for a long journey. You would also face the problem of isolation. You would be far from home, far from help. If something went wrong, you would be on your own. You would need to be self-sufficient. You would need to be prepared. You would need to be resilient. You would also face the problem of uncertainty. The black holes move. Their mazes shift. What was safe becomes dangerous. What was a trap becomes an opportunity. You would need to adapt. You would need to be flexible. You would need to be creative. You would also face the problem of chaos. Some regions are chaotic, unpredictable, where small changes lead to large effects, where prediction is impossible. You would need to avoid these regions, or navigate through them carefully, very carefully. But what if you succeeded? What if you navigated through the black hole maze? What would you learn? What would you discover? You would learn about gravity, about space and time, about the universe itself. You would push the limits of physics. You would expand human knowledge. You would also prove that it's possible, that black hole mazes can be navigated, that they can be outsmarted, that human ingenuity can overcome cosmic challenges. You would inspire others. You would open new possibilities. You would change the future. But the reality is harsh. Navigation through a black hole maze would be incredibly difficult, nearly impossible.
The challenges are enormous. The dangers are real. The risks are high. Success would require everything: perfect planning, perfect execution, perfect luck. But it might still be possible. In the far future, with advanced technology, with better understanding, with more knowledge. The paths exist. They follow the laws of physics. They're calculable. They're navigable. With enough time, enough resources, enough determination, you might just be able to outsmart the black hole maze. Chapter 6: The Mysteries We're Still Solving. The Future of Black Hole Science.
Scientists are still learning about black holes. Every year, new discoveries are made. New mysteries are uncovered. New questions are asked. The study of black holes is ongoing. It's exciting. It's fascinating. It's full of wonder. Recent discoveries have revealed new types of black holes. Intermediate mass black holes. Black holes that are larger than stellar black holes but smaller than supermassive ones. They might be hundreds or thousands of times the mass of the Sun. We're not sure how they form, but they might exist. And they would create their own mazes, their own challenges. Scientists have also discovered something called black hole morsels. These are tiny black holes, much smaller than stellar black holes. They might be created during black hole mergers. When two black holes merge, they might create tiny fragments. These fragments would be incredibly hot. They would emit radiation. They might be detectable. Scientists are looking for them. They're searching for bursts of high-energy radiation, gamma rays, neutrinos, signs that these tiny black holes exist. If they do, they would add another layer to the maze, another type of black hole to navigate around, another challenge to overcome. There's also the possibility of primordial black holes that formed in the very early universe, before stars existed. They would have formed from density fluctuations, from the chaos of the Big Bang. Some scientists think these might be dark matter, that they might be everywhere, that they might be part of the cosmic maze we don't even see. This is still just a theory, but it's fascinating. It suggests the maze might be even more complex than we think, that there might be invisible black holes everywhere, creating gravitational mazes we can't detect, that we can't navigate, that we can't understand. Recent observations have also revealed new details about black hole mergers. The LIGO and Virgo observatories have detected dozens of mergers. Each one teaches us something new. Each one reveals new aspects of black hole physics. Each one helps us understand the mazes better. In January 2025, LIGO detected something special, a merger called GW25014. This wasn't just any merger. It created the clearest gravitational wave signal ever detected. The signal was so strong, so clear, scientists could measure it with incredible precision. They could test Einstein's theory. They could confirm Hawking's predictions. The signal-to-noise ratio was about 77 to 80. That's incredibly high. Most signals are much weaker, maybe 10 or 20. But this one was crystal clear. It was like listening to a perfect note. After all the noise, all the static, this signal stood out. It was beautiful. It was clear. It was perfect. This merger confirmed something Hawking predicted 50 years ago, his area theorem. It says that when two black holes merge, the new black hole's surface area must be larger than the sum of the two original ones. It can't get smaller. It can only grow or stay the same. This is like a law of physics, a rule that black holes must follow. Scientists had been trying to test this for decades. but they needed a clear signal, a precise measurement. GW25014 gave them that. The new black hole's surface area was definitely larger. Hawking was right, again. This confirmed that black holes follow thermodynamic laws, that they have entropy, that they're not just simple objects, they're complex, they have structure, they follow rules, rules that help us understand the maze. It's amazing to think about how our understanding has changed. Over 200 years ago, John Mitchell imagined dark stars, but he had no way to prove they existed. Then Einstein's theory made them possible, but even Einstein doubted they were real. Then scientists proved they could form. Then we detected their gravitational waves. Then we saw one with our own eyes, well, with telescopes, but we saw it. The journey from imagination to observation took over 200 years. Each scientist built on the work of others. Each discovery opened new questions, and the journey continues. The detection of gravitational waves has opened a new window into the universe. We can now study black holes in ways that were impossible before. We can detect their mergers. We can measure their properties. We can map their gravitational fields. We can understand their mazes better. Recent discoveries have also revealed new details about event horizons. The Event Horizon Telescope has taken the first image of a black hole, the supermassive black hole at the center of the galaxy M87. The image shows the event horizon, the shadow of the black hole, the edge of the maze. This image is historic. It confirms our theories. It shows us what we've been imagining. It makes black holes real, tangible, understandable. It helps us see the maze, to understand its boundaries, to navigate it better. The scientist who led this project was Shep Doeleman. He said, "We've seen what we thought was unseeable. We've taken a picture of a black hole." It took hundreds of scientists working together, telescopes all around the world, years of work, and a computer scientist named Katie Booman created the algorithm that turned all that data into the first black hole picture. She said no one person could have done it alone. It took a team, a global team, working together to see the unseeable. The Event Horizon Telescope is actually not one telescope. It's a network of telescopes all around the world, from Hawaii to Spain, from Chile to the South Pole. They all work together. They all observe the same black hole at the same time. This creates a virtual telescope as large as Earth itself. That's how big you need to be to see a black hole, as big as a planet. The data from all these telescopes is combined, processed, turned into an image. The result is the first picture of a black hole, a fuzzy orange ring, the glowing accretion disk, the dark shadow in the center, the event horizon, the edge of the maze. In 2022, the Event Horizon Telescope took another picture, this time of Sagittarius A star, our own galaxy's black hole. It's closer, but it's also smaller, and it's moving. The gas around it orbits in just minutes. This made it harder to image, but they did it. They got the picture. It looks similar to the M87 black hole, a fuzzy orange ring, the same structure, the same physics. This confirmed that black holes are similar, no matter their size. They all have event horizons. They all have accretion disks. They all create the same kind of maze. Doeleman said that seeing these images was like seeing a new continent for the first time.
It opened up a whole new way of studying black holes, a whole new way of understanding the maze. Before, we could only detect black holes indirectly, through their effects on nearby stars, through their gravitational waves. But now, we can see them, directly, with our own eyes. Well, with telescopes, but we can see them. That's amazing. Recent discoveries have also revealed new details about accretion disks. Disks of hot gas falling into black holes. These disks are bright. They emit light, X-rays. They're beautiful. They're also complex. They create their own dynamics, their own challenges, their own parts of the maze.
But sometimes, black holes don't just slowly eat gas. Sometimes they have huge outbursts. In 2018, scientists detected the brightest flare ever seen from a black hole. It was 10 billion light-years away. Incredibly far. But it was so bright we could see it. It was as bright as 10 trillion suns. That's hard to imagine. 10 trillion. That's a 1 followed by 13 zeros. All that light from one black hole. What caused it? A star got too close. The black hole's gravity tore it apart. This is called a tidal disruption event. The star was stretched, pulled apart, turned into a stream of gas. That gas fell into the black hole. It heated up. It glowed. It created the brightest flare we've ever seen. The flare peaked over 3 months. Then it slowly faded. But we're still watching it, still learning from it, still understanding how black holes eat, how they create these cosmic fireworks, how they add drama to the maze. These tidal disruption events are rare, maybe 1 per galaxy per 10,000 years. But when they happen, they're spectacular. They teach us about black holes, about how they interact with their surroundings, about how they create the maze. Scientists are searching for more of these events, using new telescopes, new detectors. They want to understand them better, to see what they can teach us about black holes, about gravity, about the universe. Recent observations have also revealed new details about jets, narrow streams of particles ejected from black holes, at nearly the speed of light. These jets are powerful. They're mysterious. We're not sure how they form, but they're part of the black hole system, part of the maze. Jets are incredibly powerful. They can stretch for thousands of light years. They can travel at 99.9% the speed of light. They carry enormous amounts of energy, more energy than entire galaxies. Scientists have detected these jets using radio telescopes. They've seen them shooting out from black holes. They've mapped their structure, but we're still not sure exactly how they form. Scientists have observed something strange about jets. They wobble. They move back and forth. In 2019, astronomers watched a black hole called V404 Cygni. It's a stellar black hole, about 9 times the mass of our Sun. It's relatively close, only 7,800 light-years away. Scientists saw its jet wobbling, moving back and forth, on timescales of just minutes. This is incredibly fast. The jet was changing direction rapidly. Why? Because of something called the lens-tethering effect. The black hole is spinning. It's dragging space around it. This warps space-time. This makes the jet wobble, like a spinning top. This was the first time scientists saw this effect so clearly. It showed how black holes warp space, how they create the gravitational maze, how even their jets are affected by the curvature of space.
In 2024, scientists discovered something else about V404 Cygni. It's part of a triple star system, 3 stars orbiting each other. The black hole is one of them. This is rare. Most black holes are in binary systems, just 2 objects. But this one has 3. This tells us something about how black holes form, that they don't get kicked out of their star systems, that they stay close to where they were born, that they can be part of complex systems, that the cosmic maze can have multiple layers, multiple objects, multiple challenges. Some scientists think jets form when magnetic fields get twisted by the black hole's rotation. The spinning black hole drags space around it. This twists the magnetic fields. The fields get stronger. They channel particles. They shoot them out like a cosmic particle accelerator. But this is still a theory. We're still learning, still observing, still trying to understand.
Jets would be a major hazard for navigation. If you got too close to a jet, you would be hit by particles moving at nearly the speed of light. These particles would be incredibly energetic. They would damage your spacecraft. They would be dangerous to life. You would need to avoid jets or shield yourself from them. But shielding would be difficult. The particles are so energetic, so fast, so powerful. Navigation would need to account for jets, to map them, to avoid them, to understand them as part of the maze. Recent discoveries have also revealed connections between black holes and other cosmic phenomena. Gamma-ray bursts, gravitational waves, neutrino bursts. These connections help us understand black holes better. They help us understand the universe better. But there are still mysteries, many mysteries. Questions we can't answer yet. Questions that drive scientists to keep studying, keep exploring, keep learning. What happens inside a black hole? What's at the singularity? We don't know. Our theories break down. Physics as we know it stops working. We need new theories, new understanding, new ways of thinking. What happens to information that falls into a black hole? Is it lost forever, or is it preserved somehow? The information paradox is one of the biggest mysteries in physics. We're still working on it. We're still learning. This paradox was created by Stephen Hawking. In 1974, he said information that falls into a black hole is lost forever. This created a huge problem, because quantum mechanics says information can't be destroyed. But general relativity says it is. For decades, scientists argued about this. Then, in 2004, Hawking changed his mind. He said, "I was wrong." He now thought information is preserved. It's encoded on the event horizon. Even the greatest scientists can change their minds. That's how science works. We learn, we discover, we change our understanding. Hawking's change of mind was a big deal. He had been defending his original idea for 30 years. He had debated other scientists. He had written papers. He had given talks. But then he changed his mind. He said the information isn't lost. It's encoded on the event horizon. It's preserved. This was a relief to many scientists. It meant quantum mechanics and general relativity could work together. They didn't have to conflict. They could both be right. But not everyone agrees. Some scientists still think information is lost. They think Hawking was right the first time. They think black holes really do destroy information. They think we need new physics to understand this. The debate continues. Scientists are still working on it, still learning, still exploring.
The information paradox is one of the biggest unsolved problems in physics. It's a mystery, a puzzle, part of the black hole maze that we're still trying to understand. Interestingly, recent discoveries have added new twists to this debate. In 2025, scientists confirmed something Hawking predicted. They observed that the surface area of a black hole's event horizon can never decrease. This was confirmed by watching two black holes merge. The new black hole had a larger event horizon than the two original ones combined. This confirmed Hawking's area theorem. It showed that black holes have entropy, that they follow thermodynamic laws, that they're not just simple objects, they're complex. They have structure. They might preserve information after all. How do supermassive black holes form? They're too large to form from single stars. They must have grown. But how? Through mergers? Through accretion? Through something else? We're not sure. We're still learning.
But recent discoveries are giving us clues. In 2023, scientists found the most distant supermassive black hole ever seen. It's in a galaxy called UHZ1. It's 13.2 billion light-years away. That means we're seeing it as it was 13.2 billion years ago, just 450 million years after the Big Bang. The universe was young, very young. But this black hole was already huge, between 10 and 100 million times the mass of our Sun. How did it get so big so fast? Scientists used the James Webb Space Telescope and the Chandra X-ray Observatory to find it. They saw the X-rays it emits. They measured its mass. They confirmed it exists. This discovery challenges our ideas about how black holes form. They must have grown incredibly fast, or they must have started huge, or both. We're still trying to understand. In 2024, scientists found another clue. They discovered a supermassive black hole forming in an unusual place, between two colliding galaxies. These galaxies are called the infinity galaxy because they look like the infinity symbol. Each galaxy already has a black hole at its center, but there's a third black hole forming between them in the chaos of the collision. This is strange. Black holes usually form at the centers of galaxies, not between them. But the collision created extreme pressure. It compressed gas clouds. It triggered the direct collapse of matter into a black hole. This shows that black holes can form in unexpected ways, in unexpected places, that the cosmic maze can have surprises, that nature finds creative ways to create black holes, that we still have a lot to learn. What about white holes? The theoretical opposite of black holes. Regions where nothing can enter, only exit. Do they exist? Could they be part of the maze? We don't know. They're purely theoretical, but they're fascinating. Some scientists think white holes might be connected to black holes, that a black hole might eventually turn into a white hole, that information might escape through a white hole. But this is just a theory. We've never detected a white hole. We've never seen one. They might not exist, but they're interesting to think about. They're part of the theoretical maze, the maze of ideas, the maze of possibilities. In 2025, new research suggested something even more interesting, that black holes might transition into white holes, that they might eject matter back into the universe, that they might even eject time. This is a revolutionary idea. It connects black holes to dark energy, the mysterious force that's making the universe expand. The research suggests that dark energy might be used to measure time. That time itself might be connected to black holes, to white holes, to the cosmic maze. This is still very theoretical, very new, very controversial, but it shows how scientists are thinking, how they're exploring, how they're trying to understand the maze, even the parts we can't see, even the parts we can't understand yet. But while we're exploring these theoretical ideas, we're also making real observations. In 2025, scientists observed something incredible: a white dwarf star orbiting very close to a supermassive black hole. The white dwarf is in a galaxy called 1ES 1927 plus 654. It's 270 million light-years away. The white dwarf is small, only 10% the mass of our Sun, but it's orbiting the black hole, very close. So close that it's traveling at nearly half the speed of light. That's incredibly fast. The XMM Newton telescope detected X-ray flashes from the white dwarf. The flashes are getting more frequent. This means the white dwarf is getting closer. Its orbit is shrinking. The black hole is pulling it in, slowly but surely. The white dwarf's outer layers are being stripped away, eaten by the black hole. This is stabilizing its orbit, for now, but eventually it will fall in. It will become part of the black hole. This observation shows us what happens when objects get too close, when they enter the dangerous zone, when they become part of the maze. It's a real-time demonstration of how black holes eat, how they grow, how they create the cosmic puzzle. What about wormholes? Theoretical tunnels through space-time, connecting distant regions. Could they be part of the maze? Could they provide shortcuts? We don't know. They're also theoretical, but they're also fascinating. Wormholes are like shortcuts through space. Instead of going around a black hole, you could go through it, through a tunnel, to another part of the universe, or to another universe entirely. Kip Thorne has studied wormholes. He's calculated that they might be possible, but they would be unstable. They would collapse quickly, unless you had exotic matter, matter with negative energy, matter that we've never seen, but might exist. If wormholes exist, they could be part of the maze. They could provide shortcuts. They could change everything. But we don't know if they're real. We're still exploring, still learning, still imagining. Some scientists think black holes might be wormholes, that when you fall into a black hole, you don't hit a singularity. You go through a tunnel, to another place, another time, another universe. This is called the ER equals EPR conjecture. It's a connection between wormholes and quantum entanglement. It's a way to solve the information paradox. But it's still just a theory. We don't know if it's true. We're still exploring, still learning, still trying to understand the maze. These mysteries drive scientists. They inspire curiosity. They lead to new discoveries. They make the study of black holes exciting, fascinating, full of wonder. The future of black hole science is bright. New telescopes, new instruments, new techniques. We can see more. We can understand more. We can learn more. The James Webb Space Telescope will study black holes in infrared light. It will reveal new details, new structures, new mysteries.
It will help us understand the mazes better. The James Webb Space Telescope is already making discoveries. It's observing black holes in distant galaxies. It's seeing how they affect their surroundings, how they shape the galaxies around them. It's detecting light from the early universe, from when the first black holes formed. This is helping us understand how black holes grow, how they evolve, how they create the mazes we see today.
The James Webb Space Telescope is revolutionary. It can see infrared light, light that's been stretched by the expansion of the universe, light from the very early universe, from when the first galaxies formed, from when the first black holes appeared. This is like looking back in time, seeing the universe as it was billions of years ago. The telescope has already found black holes in the early universe, black holes that shouldn't exist, that are too big, that formed too fast. These discoveries are challenging our theories. They're making us rethink how black holes form, how they grow, how they create the cosmic maze. But the James Webb Space Telescope isn't just finding black holes, it's studying them. It's seeing how they affect their galaxies, how they shape star formation, how they create winds, how they influence evolution. It's like having a time machine, a way to see the universe's history, a way to understand how the maze evolved, how it grew, how it became what it is today. Scientists are also planning new missions. The LISA mission will launch in the 2030s. It will detect gravitational waves from space. It will be more sensitive than LIGO. It will detect smaller black holes. It will detect mergers from farther away. It will map the gravitational maze in ways we've never done before. It will open new windows into the universe, new ways to understand black holes, new ways to navigate the cosmic maze. The LISA mission will detect gravitational waves from space. It will be more sensitive than LIGO. It will detect more mergers. It will reveal new aspects of black hole physics. It will help us map the mazes better. New ground-based telescopes will study black holes in visible light, in radio waves, in X-rays. They will reveal new details, new structures, new mysteries. They will help us understand the mazes better. Computer simulations are also getting better. More powerful computers, better models, more accurate physics. They can simulate black hole mergers. They can simulate accretion disks. They can simulate the mazes. They can help us understand what we observe. Scientists use supercomputers to simulate black holes. They calculate how space curves, how matter falls in, how gravitational waves are created. These simulations are incredibly complex. They require billions of calculations. They take days or weeks to run, but they are getting better, more accurate, more detailed. They're helping us understand the maze, to map it, to navigate it, at least in theory. Some simulations show that black hole mazes are even more complex than we thought, that there are paths we haven't discovered yet, that there are shortcuts, that there are traps, that the maze is constantly changing, evolving, creating new challenges, new opportunities. These simulations are like practice runs. They let us explore the maze without actually going there. They let us test navigation strategies. They let us understand the physics. They're tools, tools for understanding, tools for exploration, tools for navigating the cosmic maze. But simulations have limits. They're based on our current understanding of physics.
If our understanding is wrong, the simulations will be wrong too. They're approximations. They can't capture everything. They can't show us what we don't know. But they're still useful. They still help. They still teach us about the maze, about black holes, about the universe. They're part of the journey, part of the exploration, part of the wonder. But there's still more to discover, more mysteries to solve, more questions to ask. The journey continues. The exploration continues. The wonder continues. Black holes are mysterious, but they're also understandable. They follow the laws of physics. They create patterns. They create mazes. And with enough knowledge, enough skill, enough technology, we might just be able to navigate through them. We might just be able to outsmart the black hole maze.
The study of black holes is like learning to read a map. But the map is three-dimensional, and it's constantly changing. And the paths are determined by gravity, by the curvature of space, by the laws of physics. It's a complex puzzle, but it's also beautiful. It's a testament to the power of gravity, to the structure of space and time, to the universe itself. Black holes are mysterious, but they're also fascinating. They're beautiful. They're part of the universe, part of the cosmic puzzle, part of the maze. And understanding them helps us understand the universe, helps us understand ourselves, helps us understand our place in the cosmos. And now the stars begin to dim behind your thoughts. We've drifted through 100 quiet truths, from the event horizons that mark the boundaries of black holes to the gravitational mazes that curve through space, from the binary systems that create complex paths to the mysteries we're still solving, from the theoretical possibilities to the practical challenges of navigation. You've wandered through cosmic puzzles. You've explored gravitational mazes. You've learned about the physics of black holes and the challenges of navigation. You've discovered the complexity of black hole systems, the beauty of curved space, the wonder of the universe. You are a part of this universe, not just a passenger on Earth, but a participant in its long and luminous unfolding. The atoms in your body were forged in stars, the same stars that can become black holes. You are connected to these cosmic puzzles, to these gravitational mazes, to these mysteries. Tonight, as you rest, black holes are merging somewhere far away. Their gravitational waves are traveling through space. Their mazes are evolving. Their puzzles are changing. The universe is full of these cosmic challenges, full of these mysteries, full of these wonders. You are floating within it, a small warmth in the dark, resting in the spiral arm of a quiet, radiant sea, surrounded by the gravitational fields of black holes, connected to the cosmic puzzles, part of the universe, part of the mystery. If you happen to still be awake, you can go ahead and watch the next video. But if you're drifting off, that's perfect too. The black hole mazes will still be there, still curving through space, still creating puzzles, still full of mystery. Sweet dreams, and keep looking up at the stars. Remember, every time you think about black holes, you're thinking about some of the most mysterious objects in the universe. Objects that create gravitational mazes, puzzles that challenge our understanding, mysteries that inspire wonder. That's pretty special. Good night.